that time. It's time for our virtual answer key for your test for related rates and implicit differentiation. Let's get right into it. Number 1 and 2 are pretty straightforward. We want to find dy dx, so we need to take derivatives with respect to x. So that means here that we have 4x cubed, that's going to become 12x squared. We don't do any dx, dy, any of that kind of term because we're doing it with respect to x. Same thing here, this will become a 12x. This term will become a 10y to the fourth dy dx, because, like I said, we need to do it with respect to x, minus, this will be a 6y dy dx. And then on this side, the derivative of 0 is just 0. So that's pretty straightforward there. Now, we want to bring these two terms without the dy dx, bring those to the other side. So we'll end up with 10y to the fourth dy dx minus 6y dy dx. Those are going to stay on this side. Equals, we'll have a minus 12x squared and a minus 12x on the other side. Factor out dy dx on the left. We'll be left with 10y to the fourth minus 6y. So we still have negative 12x squared minus 12x on the right. And then we're going to divide to get dy dx by itself. So dy dx will equal negative 12x squared minus 12x over 10y to the fourth minus 6y. Now from there, just can we simplify it a little bit? I can pull out a negative 12x up top, and I'd have x plus 1 left. And on the bottom, I would have a, if I pulled out a 2y, I would have y cubed minus 3 left. So that's how you will get your answer right there. And we can take it one step further to cross out a 12 and a 2. So I have a negative 6x, x minus 1 up top, and on the bottom, y times quantity, y cubed minus 3. So again, if you can get to here, that's great. If you can see to simplify to there, that's even better. Okay, number 2. This one, again, we'll have 2x for the first term. We'll have 2y dy dx for the second term. And then for the right-hand side, we're going to have a little bit of product rule going on right here. So first times derivative of the second. We're going to say 2x is my first. So 2x times derivative of y is dy dx. Plus the second, which is y, times the derivative of 2x, which is just 2. So 2y. Get all terms where they belong. We're going to bring the dy dx to the left. So I'll have 2y dy dx minus 2x dy dx on the left. And on the right, I'm going to have 2y minus 2x. Factor out dy dx, dy dx. I'll have a 2y minus 2x left on the left, and a 2y minus 2x on the right. From there I divide, dy dx equals the division, 2y minus 2x over 2y minus 2x. Well, that's the same thing, which means that dy dx is just equal to 1. Will it simplify that easily tomorrow? No, but a lot of things probably will cancel out for sure. Alright, number 3. This one, we're now no longer looking for dy dx, now we're into the dy dt and dx dt. So we need to take derivative of everything with respect to t. So derivative of x squared is 2x dx dt. Derivative of y squared is 2y dy dt. And the derivative of 289 is 0. Now we plug in what we know. So dx dt equals 4, so I'll plug that in. X is 15, so I'll plug that in. And what else do we know? That y is equal to 8. So we want to find dy dt. So equal to 0. And from here, it's just, can you solve an algebra problem? So you end up getting this is 16 dy dt will equal, if I bring this over to the other side, it's negative 120 when I do the multiplication. Then divide by 16, dy dt will equal negative 15 over 2, or negative 7.5 for your answer for number 3. Now, into the word problem. Starting with the square, I'm going to tell you right there, area equals side squared. That means when I do the derivative, dA dt will equal 2s ds dt. We always have to do with respect to time. And what do we know? We know that The side is 10 feet long. That's when we want to look at it. So 2 times 10 times what is the change, the DSDP, how fast is the side increasing? The side is increasing at 5 feet per second, so that's why I put 5 there. So my answer here, 2 times 5 times 10, 100 is my numerical answer. Remember, dA dt, area would be in feet squared, and time here is in seconds. So feet squared, actually, I'm sorry, it is not seconds, it is minutes. So feet squared per minute for that one. Number 5, we're now looking at a cube. So the walls of a cube increasing at a certain rate, or in this case, decreasing on our Star Wars characters here. Same thing, tells us volume equals the side cubed. That means, because the side is always changing, we have to take a derivative immediately. dV dt equals 3s squared ds dt. What things do I know? We want to know when the width is 6 meters. So I will plug in 6 for s. What else do we know? We want to know at what rate is the volume changing. So dV dt again is our unknown. That means we should know ds dt. So the walls are closing in at 5 meters per minute. So this becomes 5 right here. So 3 times 6 times 5. However, they're closing in. It's decreasing. So this should be a negative 5 for ds dt. So when I plug all that in, I'm going to end up with negative 540. And again, my unit, volume per time. Volume is cubic, and time in this case is minutes. So meters cubed per minute. That's why that's our unit for number 5. Number 8, now we have the circle. Again, tells us we're looking at the area of a circle, so area equals pi r squared. The radius is changing, that's the only variable we're looking at, so we have to take the derivative immediately. dA dt will equal 2 pi r dr dt. Again, what is it that we know? The area is growing at 20 square millimeters per second. Area is growing, dA dt. It's growing, so it's positive, so dA dt is 20. 2 pi, what is the radius? We want to know what the radius, or what dA dt is when the radius is 8 millimeters. So we'll plug in 8 here, dr dt. Solve for this, we're just going to divide, so we'll have 20 over 16 pi is what will equal dr dt. Simplify that a little bit here, and I can make this 5 over 4 pi. My unit will be its radius over time. The radius is in millimeters. So millimeters per, in this case, second, is equal to dr dt. Number 7, looking at the sphere. Again, another one, we have just one variable. Volume equals 4/3 pi r cubed. Radius is changing. We're looking at radius increasing, so we take a derivative immediately. dA, or dV dt is equal to 4/3 times 3, this is going to be 4. Pi is still a constant, keep it there. R squared, dr dt. Plug in what we know. The balloon is inflating at this rate. That is how much the volume is changing. So dV dt is my 2. So 4 times pi times, we want to know what it is, what this dr dt is when the radius is 3. So now I plug in my 3. dr dt is what we're looking for. dr dt. So from there, let's try to solve as best we can. We'll end up with 2 divided by 36 pi is equal to dr dt. Again, r over t, rate over time, or radius over time. That means that we're going to have my units as feet per minute equals dr dt. And I can simplify this instead of 2 over 8, or 2 over 6, 2 over 36 pi, 1 over 18 pi. This one. Number 8, the cone. This is the one that's going to be the trickiest of all of them. Volume equals 1/3 pi r squared h. Now, in this one, we want to see what relationship can we form between the radius and the height. Well, the tank is 100 feet tall and the radius is 50 feet. That means that radius over height would be 50 over 100, or 1 over 2. That means that the radius is always the radius is always half of the height. or that would mean also that the height would be twice the radius. One way or the other, one of these two equations we're going to plug into this. Question is, which one? Well, what are we looking for? It says here they want the rate of change of the height. So we want to stay with h. So this is the equation I'm going to end up plugging in for r. So let's rewrite this. Volume equals 1/3 pi. Instead of r, I'm now going to put in 1/2 height squared times height again. Keep rewriting it. 1/3 pi times, this will become 1/4 h squared times h. One more simplifying, I can bring my numbers together. 1/3 times 1/4 is 1/12 pi, and now I have 3 heights, 3 h's. Now I can take a derivative. Now I have just one variable. It's time to take a derivative. This will become 3 times 1/12. It's going to be 1/4 pi, and then it's h squared dh dt when I do that derivative. Same thing now, plug in what I know. Well, so if you want to know when the height is 32 feet, so now I can plug in my 32 for the height. They want to know the rate of change of the height, so dh dt is going to stay as it is. That's what we're trying to find. Pi, 1/4. What is the volume? How's the volume changing? Well, here it is. It's being poured in at 50 cubic feet per minute. So dv dt is what my 50 is. So from there, plug and chug. I would end up with 50 over, actually, if I would multiply by 4 first, it would end up being 200 on the top, and on the bottom would be 1024 pi is equal to dh dt. And if I simplify that, I'll end up with 25 over 128 pi. And my unit again is height and time. My height was in feet, and time in this case is minutes. So feet per minute as my unit for this one. Number 9, cylinder. Cylinder should be pretty easy because remember, in a cylinder, if you want to draw the picture, the radius never changes in a cylinder. So the volume equals pi r squared height, but I can plug in this radius immediately because the radius will never change. So volume will equal 9 pi times height because I can plug in 3 for my radius. So now, again, one variable. Now I'm going to just take my derivative. dv dt will equal 9 pi. The derivative of h is 1, so we just put in a dh dt. So this one should be pretty simple. At what rate is pop flowing out of the can? That's what we want to know. That's a volume. So what else do we know? Well, we have no place to plug in a height. We don't have a radius, so we don't even have to worry about that. Just what the change in height is. It's falling, so it will be negative at a rate of 8 centimeters per minute. So negative 8 there for this one. So that means that dv dt is going to be negative 72 pi, my unit, centimeters cubed per minute, volume per time. All right, last one, so triangle problems. First, with ladder problems, always beneficial to draw a picture for this one, see what we're looking at. It's slipping down. The ladder is 10 feet long, and what do we want to know? We know that, that it is going, we want to know what it is going along the ground. We know as it's dropping, we know it's slipping at 10 feet per second. So a lot of 10s going on here. Got to make sure we're going in the right direction with everything. I'm going to set this up as A, B, and the hypotenuse being C. Always going to be doing Pythagorean theorem for this. Now, what is never changing in this problem? The 10, the ladder length is never going to change. So I can plug in that 10 immediately. A squared plus B squared will always equal 10 squared. So I can plug it in immediately. As the ladder slips, though, B and A will switch their amount. So we can't plug anything in yet. So can't do anything else. So now take our derivative, 2a dA dt plus 2b, or not 2b, dv dt, equals 0. Now, what do I know for sure? Well, the change in b is 10, but it's going down, so this should be negative 10. We know that for sure. We don't know dA dt. That's what we're trying to solve for. It's dA dt. What else do we know? Well, we have, they want to know when the bottom is 6 feet away from the wall. So when A equals 6. So I'm going to have 2 times 6 there. I'm going to have 2 times something here, but what? I can figure it out now, though. If a is 6, that means that, again, a squared plus b squared equals c squared. 6 squared plus b squared must equal my 10 squared from the ladder. That means that b is going to equal 8 in this case when I do that simplification. So now I can plug in what I know and get exactly my answer for this. dA dt will equal, this is going to become positive when I bring it over, so this will be a positive 160 divided by 12. And again, this is going to be, if it's dA dt, that'll be feet squared, or no, not feet squared, just feet per second. And if I simplify that a little bit, dA dt will equal, it should be 40 over 3, and it should be feet per second again. And this should make sense. As b is going down, my distance of a should be increasing. So positive answers should make sense for that. Okay, number 11. We're looking at the baseball field in this one. So again, it'll help you draw your picture, something like that. So here's home plate. The runner is right here. He's going from first to second. He's going this direction at 20 feet per second. This distance is always 90. Always 90. And we want to know what this distance is right here. So again, I'll call that C. They want to end up knowing what it is. If this is A, we'll call that B. So A squared plus B squared equals C squared. What do we always know? Well, that this side B is always 90. So 90 squared. We can plug it in immediately. Now I take my derivative. 2A dA dt. That'll go away. 2C dC dt. If you want to, both sides are multiplying by 2. I could even cancel out those 2's right away and just have A dA dt would equal C dC dt immediately if you wanted to. Up to you. If you want to simplify later, that's fine as well. So now that we've done our derivative, what is changing? Well, this value of A is changing. At the moment, if he's 30 feet from second base, that means he's 60 feet away from first base here, and that's the number we need to use. So A is going to be 60. It's changing at a rate of 20. What's C? Well, again, we're going to do that 60 squared plus 90 squared have to equal C squared. That means C will equal the square root of 11700, or that'll simplify to 10 square roots of 117. So over here, C is 10 root 117. We want to find dC dt. That means that in the end, dC dt will equal 60 times 20, which will end up being 1200 over 10 square roots of 117. Simplify that, I'll make it 120 over the square root of 117, my unit. C over time, so something per second. It's a distance of feet per second. Last one, 2 planes coming at each other. So here's one plane going towards the airport. Here's the other plane going towards the airport. This guy's 225 miles away. This one is 300 miles away. This is the distance they want to know. How far apart are they? Again, I'll call it C. I'll call this guy A. I'll call this guy B. And these are the rates we're looking at. We want to know how much C is decreasing. We know A is decreasing at a rate of 400 miles an hour. And we know that B is decreasing at a rate of 600 miles per hour. So we have the same formula we've been using. A squared plus B squared equals C squared. In this case, all values are changing. As A and B end up collapsing, C will collapse as well. So I can't plug anything in yet. I have to plug in immediately. 2A dA dt plus 2B dB dt will equal 2C dC dt. Again, if you want to, you could cancel out your 2's immediately. However, I'm just going to leave them as they is for this one, just so you can see how you do it in this regard. We plug in now what we know. So what's changing? 2 times A at this point is 225, so I can plug it in now. Change in A, 400. Positive or negative? It should be negative because it is decreasing. This length is decreasing in the end. Same here. 2 times B is 300. times negative 600. Same reason. It is decreasing that side length. And then over here, 2 times c. Well, what is c? C we can find same way we've done before. It's with a squared plus b squared equals c squared. A is 225 squared. B is 300 squared. That means c squared is whatever's left in that right triangle. C will equal the square root of that, which when you plug in, it's 375. So 2 times c is 375 times dc dt. From there, it's just plugging into your calculator. The left-hand side, you get negative 562,500. The right-hand side, which you'll divide over, will be 750 equal dc dt. So when you do that division, you should get negative 750 for dc dt. My unit, it's a distance over time. It should be the same unit as other rates we've done. It's miles per hour. All right, so hopefully that has done you well. Hopefully this will set you up for success. Again, you won't have all of these problems tomorrow, but you should be able to do each type of problem that was in this review. Best of luck.